Hello, everyone, and welcome back to another calculus conversation. In this conversation, we're going to introduce something called implicit differentiation, and along with the chain rule covered in section 2.4, as well as the product, quotient, and other basic differentiation rules covered earlier in chapter 2, this serves as one of the final tools that we're going to equip ourselves with, and with it, we'll be able to differentiate and calculate slopes of tangent lines of pretty much every single type of curve we might be interested in, with some exception, but we'll talk about that a little bit later. For starters, what is implicit differentiation and why should we care? Well, for the majority of our mathematical careers, the object of interest has always been so-called functions. Functions are things that look a lot like y equals f of x, and in particular, we learned that their graphs have to pass the vertical line test. The natural example is the same fancy picture we've been drawing over and over again. So we have some sort of a function that does that. Call this y equals f of x. Maybe these axes are the x and y axes. And passing the vertical line test simply means if I draw a vertical line, no matter where I draw it, I'm only ever touching the graph once. In terms of this being a function, this means that it's a well-defined sort of operation. If you give it an input, there's a well-defined way to get a unique output. It's not ambiguous in any way. And for the most part, these are the functions that we've considered. We haven't spent a lot of time looking at functions or curves that don't look like functions. But at the end of the day, geometrically anyway, there are plenty of relationships that fail the vertical line test. There's actually a lot of them that do. For example, as we see down here, one of the first you might say is, what about the circle? For example, here we have a circle, radius 0, 0. Center 0, 0, radius 5. Well, if I were to draw that, observe that it might look something like this. So here's 5, we go up to 5, left to 5, down to 5, and maybe this becomes the circle of interest. Now, of course, when you draw this, the issue you're going to run into is that really, for most vertical lines, you're going to be hitting twice. So this relationship, as drawn here, this fails the vertical line test. However, it doesn't mean calculus can't still be asked. For example, if I were to focus on a particular point of the graph, maybe right down here, I can still ask a question about the tangent line, which still exists perfectly well. There's no reason that tangent line doesn't exist. So a question that you might ask yourself is, slope of tangent line? It's a perfectly reasonable geometric question, but the issue is that if I take a look at this relationship right here, this is not a function. This is not of the form y equals f of x. It just doesn't look like that whatsoever. It's not a function. But there's still a reasonable set of circumstances where you care about the slope of tangent lines. So you can't talk about something like f prime of x or y prime or something like that, because that's just not how this relationship is represented. So we have to be a little bit more crafty. We have to be a little bit more careful about how we find our derivative. And that's what we're going to do in this conversation. It turns out the solution is implicit differentiation. And we need it specifically to find the slopes of curves for which the vertical line test is failing. Now, of course, if I can't write my curve as y equals f of x, it's probably reasonable to note that the Newtonian notation f prime is probably no good. But it turns out the Leibniz notation d dx is really good. So this is an instance where we're going to lean heavily on Leibniz. And so what we're going to be asking ourselves is we're going to be trying to be computing the slope of tangent lines, and equivalently, using Leibniz notation, what we're interested is in the dy dx. This right here is the derivative. I should probably put this in blue. I want to be absolutely clear here, by the way. This object right here, as written, this is a function. This is in no way a number. If you wanted to evaluate this at some sort of an input, you'd have to sort of use a vertical bar and then evaluate at a point. This is going to matter pretty soon, but I'll revisit that when we get there. Now you may ask yourself, to find dy dx for curves that fail the vertical line test, why is this called implicit differentiation? Well, it turns out that there is some naming system here that says that if you can write it as y equals f of x, that is, right down over here, if you can write it as y equals f of x, we say that the relationship is given explicitly. However, if it is not possible to solve for y, then we say the relationship is given implicitly. And so for the purposes of today's conversation, this is the situation we're interested in. And it turns out that with good use of the chain rule and Leibniz's notation, we can proceed. And so what we're going to do is we're going to do the following. We're going to treat d dx as an action. And we've talked a little bit about this before. When I say something like d dx of x squared, this is an action. I am differentiating x squared. And the key here is going to be the algebraic notion that whatever you do to one side, you have to do to the other. And at the end of the day, implicit differentiation is going to boil down to really careful bookkeeping. That's kind of true for all of Chapter 2, but it's particularly true here. So what we're going to do is we're going to treat d dx as an action, we're going to differentiate both sides, and we're going to solve for the derivative. You'll see what I mean in just a second. So to start, let's revisit that circle, x squared plus y squared. Step one is I'm going to compute the derivative, and then using that derivative, I'm going to talk about the slopes of some tangent lines. For starters, let's follow this course of action. We're going to d dx, both sides, and then solve for the derivative. So let's take a look. This is how I might write it. I'm going to say x squared plus y squared equals 25 is the same as saying, well, I'm going to differentiate both sides. And this is where it's very important that you're writing d dx, because that's telling us what variable we care about here. So what happens here, okay, on the left I'm going to be very pedantic here. This is d dx of x squared plus d dx of y squared is equal to d dx of 25. This object, the way you should think about it is you want to zoom in on the function and ask yourself very quickly, what's the derivative of x squared? To which your answer should be 2x. And then for bookkeeping purposes, we're going to very explicitly let the reader know that what I've done here is I have differentiated an x variable with respect to x. So this is using the chain rule. I've differentiated the square function, that was this, and then I go in a layer, all that's left is x. So when I go in a layer, I'm differentiating x with respect to x. So just to be clear, this entire portion turns into that. Over here on the right, we have d dx of y squared. I do the same thing. I say, very quick, what's the derivative of y squared? To which you'd say, oh, it's 2y, which is good. And then when you go in a layer, you're saying, okay, I've differentiated what variable? In this case, I've differentiated y with respect to x. So this bit turned into that. And over here on the right, if I differentiate 25, well, that's a constant. So the derivative of a constant is just 0. Technically speaking, I differentiated, in this case, say x with respect to x, although it won't matter because anything times 0 is 0. But to be careful, we're going to say all of that turned into this. Now, sometimes your book won't actually write these dx over dx's. To me, I like to be incredibly consistent. I just put them everywhere. It's letting the reader know what variable I've differentiated. And of course, though, if I think of this as a number, dx over itself, dx, it's not too hard of a stretch of the imagination that this should be a 1 and this should be a 1. But this thing is not a 1. That's what we're looking for. That is the derivative. So this is going to turn into 2x plus 2y times dy dx is equal to 0. And the objective is going to be solve for dy dx. And so if I think of that as just its own variable, I might get 2y dy dx is equal to negative 2x. And then if I divide, I'm going to get 2 dy dx is equal to negative 2x over 2y, which is negative x over y. And I want to be clear here. This whole thing, as written right here, this is a function. Because what we need to do now that we figured out what the derivative is I need to talk about the slopes of the tangent lines at these points. Okay, over here on the right, I'm actually going to draw a picture. So let's redraw my circle of radius 5. There we go. And it seems like the points in question are 0, 5, 5, 0, and 3, negative 4. So that might be right here. So the tangent lines I'm interested in are that one, which is horizontal, this one, which is vertical, and this one, which is sort of positive, but not too positive. Let's take a look at this horizontal one first. If this is the derivative, I might say something like this. Thus, at the xy coordinate corresponding to 0, 5, the slope of the tangent line is, it's going to be dy dx, which is negative x over y, except I'm going to plug in a 0 for x and a 5 for y. Here's what some people do. They simply say this is negative 0 over 5, which is a 0. But this is a problem, because as written, this is a function, this is a number. A function and a number are not equal to each other, unless it's a constant function, but here it's not. So you have to be very, very careful with what you mean. And so in this case, what I'm really trying to say is that I don't want this function to be equal to 0. I want this function evaluated at xy equals 0, 5. This function evaluated at xy equal to 0, 5. Now this is true, because this object on the left is a number, and the object on the right is a number. And if you do take a look at this, it seems like the slope of the tangent line was 0. Well, that's the slope of a horizontal tangent line. So in this case, math checks out. We're going to do the other 2 points. We're going to say at xy being, say, 3, -4. The slope is, we're going to take dy dx. Again, we're evaluating it at this very specific point. That's going to be -x over y evaluated at 3, -4. And so that's going to be -3 over -4, which is a positive 3/4. And that kind of matches with what we had right here. So it looks like the picture and the math here are in fact matching up. We'll do the last one. At xy equal to 5, 0, the slope is, well, again, it's going to be dy dx, but this time evaluated at 5, 0, which is -x over y evaluated at 5, 0. And this is going to be a problem because we're going to end up with, what, -5 over 0? And that's a problem because we can't divide by 0. And you may say to yourself, wait a minute, isn't this undefined? And the answer is kind of, but in this case, the way it ends up turning out, as we see here, the slope here is infinite. The rise over run here, the rise is infinity and the run is whatever it wants to be. Either way, infinity is being hit first. And if you do take a number like 5 and you divide it by numbers really close to 0, you are getting closer and closer to infinity. And so in this case, the answer really is infinity. Where in this case, positive and negative infinity is equivalent, but in the purposes of the book and for some folks in our conversation, you could just say D and E if you want. I'm pretty flexible, don't really care. But either way, this is sort of the game and how it operates. So we're looking back at that same example before. We did the implicit differentiation over here on the left, and then we figured out how to compute slopes of tangent lines. Where the important thing here to note is we could not have done this whole tangent line question using any of our previous tools. We had to have this new form of differentiation. And really, this is true for anything that fails the vertical line test. For example, here I have y squared equals x. This is a parabola, but a parabola in terms of y. So instead of y equals x squared, it's x equals y squared. The way this is going to end up looking is it's going to be a parabola, but in the x direction instead of the y direction. So it might look something like this. This is x equals y squared. And you can see evidently that, again, this curve fails the vertical line test. So if I want to, say, take a point right here and actually ask questions about the slope of the tangent line at that point, well, I'm going to have to use implicit differentiation. And the way that's going to work is the same as before. Here I have y squared equals x. This is going to be the same as I'm going to ddx both sides. On the left-hand side, the derivative of y squared is 2y, but I'm letting the reader know I've differentiated the y variable with respect to x. And on the right-hand side, the derivative of x is just the 1, and I'm letting the reader know I've differentiated the x variable with respect to x, where we'll make the casual note that clearly something divided by itself is a 1. So what I'm left with here is that 2y times dy dx is equal to 1, or equivalently, dy dx is equal to 1 over 2y. And if you want, you could try to estimate some values and check some points and stuff like that, whatever you feel like doing. But sort of the goal at this point is going to be to get more comfortable with this process of differentiating both sides. To that end, let's take a look at a bunch of examples. So to sneak up on that and increase the difficulty, we're going to begin by just looking at like one of these sides, where we're going to try to get good at just differentiating that one side. Then we'll look back again at two-sided implicit differentiation. And sometimes things can get a little complicated. For example, here I have dy of xy. This right here, of course, is a product. So I'm going to be very careful with how I write this. This is going to be, leave the first alone, differentiate the second, plus differentiate, oops, yeah, I made a mistake right out there. It's not d dx, it's d dy. So this is differentiate the first, leave the second alone. Here I get x times, okay, what's the derivative of y? Right off the bat, we know it's a 1, and then I'm going to let the reader know that I've differentiated the y variable with respect to y. And then here, the differentiation of x is again just a 1, but now I'm letting the reader know I've differentiated the x variable with respect to y. Where again, this just turns into a 1, no problem. And what we're left with now is just x plus y dx dy. So the goal here is to illustrate that sometimes you need things like the product rule, as we'll see down here, the quotient rule, and that sometimes you need to be a little well-versed in the variety of different variables that could be at play. I think the correct way and sort of the way to get used to doing this is careful bookkeeping. Show all the steps that you need to show. So that was a product rule. Here, you're going to have a quotient rule, and I'm going to again just start out and just showcase all those steps. So this is going to be low d high minus high d low all over low squared. And so this might turn into, well, the w squared and the z cubed just kind of go along for the ride. And then we're left with this. Okay, the derivative of z is a 1. The derivative of a 3 is just 0, so that won't matter. And then we're letting the reader know I've differentiated the z variable with respect to w. So if it helps, this entire bit turned into that. Similarly over here, I get minus z plus 3. What do I get here? This is going to be the derivative of w2 or w squared is 2w, and then I'll let the reader know I've differentiated w with respect to itself. Then the derivative of z squared is 2z, where I'll let the reader know I've differentiated the z variable with respect to w. And so this entire derivative became that entire bracketed bit, where, again, we run into the situation where dw is just a 1. So you can simplify that, but I just like to be very explicit in what I'm writing. And so this might be our final answer. And remember, the context here is everything we're doing here might be just one of the two sides of a relationship for a curve that is failing the vertical line test. So once you set all this up on one side, now you might have to do some intense algebra to, say, solve for dz dw. Let's do one that involves more of the chain rule here. So what we see here right off the rip here is that this is a chain rule. The outermost function is the cube, and the innermost function is this. Ooh, and in fact, we even have a little bit of more going on here. This bit right here is going to be a product rule. So there's a lot of moving parts here. Let's take a look. So this is going to be, the derivative of the outside is going to be 3 times that thing squared, where that thing is q squared plus 2qp cubed plus p to the 6th. That's the chain rule. Then we're going to go in a layer, and we're going to get the derivative of, and you know what I'll do? I'll actually just write this out. This is ddq of q squared plus ddq of this product, and we can take the 2 out. So this is qp cubed plus ddq of p to the sixth. And then we can simplify this. So the object over here on the left, we're going to maintain. And the object on the right is going to become, well, the derivative of q squared is 2q. And again, we let the reader know I've differentiated q with respect to q. And then we're going to end up with a product rule. We're going to leave the first alone, so the 2 hangs out. Leave the first alone, differentiate the second, where we'll let the reader know I differentiated p with respect to q, plus differentiate the first, which is a 1. Again, I let the reader know I differentiated q with respect to itself, and then leave the second alone. Plus, finally, the derivative of p to the sixth is just 6p to the fifth, where again, I let the reader know I've differentiated p with respect to q. So just to highlight this, make sure we're all on the same page, this product rule turned into this entire parentheses bit. Further, we'll note that the dq's are all 1s. And therefore, if you wanted to clean this up and get a final answer, you might have this is equal to that first bit times, we're going to get 2q plus 6qp squared dp dq plus p cubed plus 6p to the fifth dp dq. Like that. And if these feel a little complicated, they are. I mean, they're on purpose, they're a little complicated so that we can showcase how difficult and complicated they might get. So this is, again, a couple of examples of just doing one side of the differentiate both sides type implicit differentiation. If we return to the example of finding the derivative for a two-sided equation, the process is much like we started today. This two-sided equation, as rewritten here, we're going to approach it and we're going to say, I'm going to ddx both sides. When I do that and I distribute the ddx over here on the left, we're going to get two product rules. So these are both product rules. That's a product, and that's a product. So this is going to start expanding really fast. So we're going to get, well, I'm going to leave the first alone, differentiate the second, which is the derivative of y is a 1, and then I'll let the reader know I differentiated y with respect to x. Plus the reverse, we'll differentiate x squared to get 2x, which I'll let the reader know I differentiated x with respect to x, and then leave the second alone. So using a highlighter again, this derivative product rule turned into that entire thing. Doing the same thing for the second bit, we're going to get minus the derivative of y squared is 2y. Then we let the reader know I differentiated y with respect to x, leave x alone. Plus, leave y squared alone, and let's differentiate x. We're going to get a 1. Let the reader know I differentiated x with respect to x. And so this entire derivative, this product rule, is exactly what we see here. And on the right-hand side, we'll get just 2x, and I let the reader know I differentiated x with respect to x. And I'll reiterate again, all the dx's are just 1s, so those are going to go away. And if I clean this up, I'm going to get what? X squared dy dx plus 2xy minus 2yx dy dx plus minus y squared is equal to 2x. And now the name of the game is we need to solve for those items, the dy dx. And it's just like any other algebraic process. Keep all the terms on one side that have dy dx, put everything else to the other side, factor it out, and isolate it. So here I'm going to end up getting x squared, and we can do this over here on the right maybe. We're going to get x squared dy dx minus 2yx dy dx. Those are the terms that I want to keep on the left, and then we'll move everything else to the right. So we're going to get 2x plus y squared minus 2xy. And the reason we do this is because now the dy dx's that I'm so interested in, this serves as a common factor on the left-hand side. So as a result, I can factor it out. I'm left with x squared minus 2yx is equal to 2x plus y squared minus 2xy. And then, of course, if I just divide, I'm going to get that my dy dx is equal to what was on the right-hand side, now divided by whatever was left over when I factored out the GCF, which is x squared minus 2yx. And there's my derivative. So even items just involving a little bit of product rules can really start to spiral out of control until you start factoring them again. We'll do one more example before we move on to a nice picture. Here again, I want to compute y prime, which of course is the same thing as just dy dx for this equation. And this is going to boil down to, again, we're going to say that this is the same as saying d dx of the left-hand side, which is 3y squared plus 5xy minus 3 to the fourth is equal to d dx of the right-hand side, which is now a little more complicated. We have 2x plus 3y. On the left-hand side, we have, at first, is the chain rule, giving me 4 comes down. We're left with the inside to the power of 3. Then we're going to multiply that by, the chain rule says I'm going to differentiate the inside. So we're going to get d dx of the first term, 3y squared, plus d dx of the middle term, which is 5xy, plus d dx of the last term, which is negative 3. And then on the right-hand side, we're going to get, well, the derivative of 2x is just 2. But then I have let the reader know I differentiated x with respect to itself. And then similarly, the derivative of 3y is 3, but I took dy dx here. And so the only bit that's going to be a little bit frustrating right now is that this middle derivative is yet another product rule. So if I'm just careful and diligent with what I'm writing, I'm going to get 4 times 3y squared plus 5xy minus 3 cubed multiplied by, let's see, the derivative of 3y squared is going to be a good 6y, but I differentiated y with respect to x, plus that product rule, which is going to be, let's pair the 5 with the x maybe. So we're going to get, leave the 5x alone, differentiate y, which is just going to be 1 dy dx, plus differentiate the 5x, I get a 5, and I took the derivative of x with respect to itself, and then I leave the y alone. Plus 0 for the derivative of a constant, and then on the right-hand side I have 2 dx dx plus 3 dy dx. Which means I'm in good shape so far. The dx dx's, of course, are just 1s. So what am I working with now? I have this object in the front times 6y dy dx, a 5x dy dx, a 5y, and then we have some numbers over here. Our goal is to get dy dx to be isolated. So what I'm going to have to do here is some really hardcore algebra. I'm going to take this and I'm going to start distributing it into my sum, and it might look something like this. 4 times 3y squared plus 5xy minus 3 cubed is being multiplied against 6y plus 5x, which had a common factor of dy dx, plus, and then I'm going to distribute this again, but now it's only going to hit that 5y from here. And on the right-hand side, I have 2 plus 3 dy dx. And then the reason I'm doing this is because now that everything is expanded and simplified, this term has a dy dx in it. This term has a dy dx in it. So I'm going to pull those on the same side and then factor out my dy dx. I might have dy dx is multiplied by, it's going to be this product minus 3, because we would move that from the other side, is equal to the 2 from the right-hand side minus whatever was left over, which is what we have right here. And so we win provided we divide both sides by this bracketed bit over here. So let's do that, and then we win. So dy dx is equal to, the numerator on the right-hand side is going to be this the previous right-hand side. And the denominator is going to be whatever was inside this bracketed bit over here on the left. And there's our derivative. So again, what we're showcasing here is that implicit differentiation boils down to a lot of pretty intense algebra, honestly. So you're going to have to practice this a lot in order to get good at it. I 100% promise you. The difficulty that we're seeing in this problem would be, for example, fair game on something like an exam or something like that. And so what we're going to close off with is we're going to close off with one last example where we have a nice picture to go along with it. So here I have some sort of an equation, y cosine of y plus t squared is equal to t cubed, where this is my t-axis, this is my y-axis. And what I want to know is the derivative at any given point. And in particular, I want to determine the equation of the tangent line at 0, 5 pi over 2. Note that 5 pi over 2, if we were to think about that as some sort of a radian output, pi is about 3.14, so 5 times 3 is like 15, 15 over 2 is something like 7 point something, so it looks like the point we're interested in is probably this one right here. And so if we were to design the tangent line at that point, it might look something like this. Not quite that. Probably something like that. And so when we think of this, and this has a name, right? We call this point P. And so we can predict that the equation of that tangent line should have a slope of, I don't know, slightly negative. Let's find out. So for starters, let's compute dy dt. So I'm going to take this equation and I'm going to hit it both sides with a d dt. That's the denominator. So we're going to say that y cosine of y plus t squared equal to t cubed. We're going to hit both sides with a d dt and then see what happens. On the left-hand side, we have an immediate product rule. So this on the left-hand side is going to become, well, let's differentiate y. We'll get 1 dy dt, and then leave the second bit alone. Then we're going to leave the y alone and have to differentiate d dt, what's left over, the cosine of y plus t squared. And on the right-hand side, we're going to end up getting just good old 3t squared, where I differentiated t with respect to itself. And so what remains is this object right here, this derivative, that's a chain rule. So it looks like what I'm considering now is a dy dt of cosine y plus t squared plus y times, let's see, the derivative of cosine is a negative sine of whatever's on the inside. Then the chain rule kicks in. The derivative of y is 1 dy dt plus the derivative of t is a 1 dt dt, and the derivative of t squared is 2t dt dt. And then the right-hand side, of course, is whatever it is. We make the natural simplification that all the dt dt's are just 1s. And what we're going to have to do is, again, very similar to the previous problem, I'm going to have to distribute this across those terms. So what this is going to look like is it's going to look like on the left dy dt times the cosine of y plus t squared. And then what we're going to get is a minus dy dt times y sine of y plus t squared. And then what we left with is this is going to distribute against the 1 plus 2t. So we're going to get minus y sine of y plus t squared times 1 plus 2t is equal to 3t squared. And the neat part about this is the objective is to simplify and get dy dt, all those terms on one side, but they're already on one side. So all I have to do is really get this object without the dy dt to be on the other side. I can do that just by moving this equal sign over here. So it's the equivalent of taking that minus and moving it to the right. That's what we have here. So what I'm going to do is I'm going to factor out that dy dt and then divide by whatever was left over. Oh, look, I committed a cardinal sin. I'm using equal signs to connect equalities. No bueno. Those need to be arrows. So what I'm getting is that dy dt is equal to whatever's on the right-hand side, which is exactly what we have here, over whatever would be left when you factor out the dy dt. So we're going to get cosine of y plus t squared minus y sine of y plus t squared. And there's our derivative. It's a little complicated looking, but no problem. In particular, if we go back to our point P, which again is the point corresponding to that line, it seems to be at the coordinate 0, 5 pi over 2. So what we're going to say is that the slope of the tangent line at the point ty equal to 0, 5 pi over 2 is, what I'm going to do is I'm going to take the derivative dy dt and I'm going to evaluate that at the point P, which is the same as taking this derivative right here and evaluating it at the point 0, 5 pi over 2. Let's simplify this. What do we get? Well, anywhere you see a t, it goes to 0. So that means this object goes to 0, this goes to 0, the insides go to 0. So what are we going to end up left with here? Upstairs, we're going to get a 5 pi over 2 times the sine of 5 pi over 2. And downstairs, we're going to get a cosine of 5 pi over 2 minus 5 pi over 2 times sine 5 pi over 2. Let's try to simplify this a little bit. I think the key thing to note here is that 5 pi over 2 is, if you were to draw it, I'll erase this in a second, we get what? Pi, well, let's phrase it this way. Pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So that means the angle in consideration here is coterminal with pi over 2. So we can see here that this number up here, sine of 5 pi over 2 is a 1, similarly down here. And importantly, this number here is a negative 1. Oops, sorry, is a 0. So that means what we're considering here is going to be a 5 pi over 2 divided by negative 5 pi over 2. So we're getting a negative 1. And what we see here is that the slope of this line, well, maybe there's a, oh, of course, yes. Okay, so we know it's negative because this is pointing downward, but of course our scale is going to be very off because here we see that for every 1 tick mark in the t direction, there's 5 in the y direction. So the scaling is a little bit stretched horizontally here, or compressed vertically, whatever you want to call it. And so what we just found is that, in fact, the slope of that line is a negative 1. Thus, the equation of the tangent line at P is, using point slope form, y minus y1, 5 pi over 2, is equal to the slope times x minus x1. And there's our line. So this is just, I think, a really fun example of using a wacky, crazy relation, which you can see just fails the vertical line test infinitely often. It's quite ridiculous looking. And yet we were able to find an equation for its slope and actually determine the slope at a point. I think a lot of the examples we did in this video are pretty complicated, so if you need to rewatch this a couple times, I think that's perfectly acceptable. But otherwise, this is going to conclude our conversation on implicit differentiation, which is a difficult tool, but a very important one, and it's one of the last ones we're going to add to our tool belt or repertoire. So take a look at the homework. Let me know if you have any questions, but otherwise, I'll catch you all in the next one.